follow the algorithm says you let the start state of the AB machine be the start state of the A machine. You remove the accept state status from the accept state of the machine on the left, and you lambda from there to the start state of the machine on the right. Okay, so this is clearly like not the most efficient way to write a machine that accepts AB. I guess in particular this thing's kind of silly, but anyway, if we're learning the algorithm, there it is. Okay, and now I do basically the same thing over here, right? So I have C and D. C is going to be this machine, which does this, cha-cha, cha-cha. D is going to be the machine that looks like this. Then I can create the CD machine, which is going to look like this, and C, and we remove the accept state status from the accept state of the C machine on the left, and we lambda from that accept state to the start state of the machine on the right, and here we go. Okay, having made these two machines, I now make the alternation of those two machines. And for that, I don't really have a plan to do this smoothly. So A, B, or C, D is the start state of my machine. What do? I immediately just lambda transition to the start states of these other machines. I might just like kind of cheat here a little bit because, you know, come on. So let's just go SAB and SCD, because those are in fact, of course, the machines are just sitting right there. And then finally, I concatenate that machine with the E machine, and the E machine is going to be SE, ja, E, and then FE, jump. Okay, so I'm just going to write kind of like etc. here, and now that leaves me space for the final answer. What's the final answer? Well, the A, B, or C, D, E machine. Do I need to go get Ada? Yes. Like now?
Yeah.
All right. Is going to go like this. It's going to start. Oh man, it's so late. Oh, this is terrible. AB or CDE machine is going to look like this, and then what's it going to do? It's going to lambda to the start state. As I got a little bit lazy over there in the second to last step, I will now get unlazy. It's going to lambda to the start state of the AB machine, which I have right here, which does an A, followed by F of A, followed by SB, followed by FB, cha, B, cha, lambda. And here we have, I guess I could write a little bigger, FA, SB, FB, and this was B. Okay, so like this whole thing was the AB machine, and now let me just say a couple more things. This is CD, this is FC, SC, FC, no, D. Okay, so then here, cha-cha-cha, what did we do? We read a C, we then lambdaed to the SC, and then that was a D. Okay, so this was the AB machine, this was the CD machine that we made in previous recursive steps. Then the OR of those two machines, which was the previous step, is a new machine, which is a new start state, which lambdas to the start states of those two machines. and then the accept states of those two machines, which are these two, were both accept states of this previous machine. But then finally, we attach E onto the end. So now, what I need to do now is I'm going to go this way. That'll be for clarity and stuff. What I now do is I remove their accept state status and lambda from them to the start state of the E machine, which takes you here, and this machine has in fact just one accept state, it's that one. So this is an extremely inefficient way to write a machine that recognizes that language, but the point is that we've followed the algorithm. Okay, good. I'm going to stop there and resume this video later.